Assalamualaikum and good day to Dr. Ali. Today, Group 13, consisting of me, Putu Aina Sofia, and Yauzin, will be presenting our second assignment for Mathematical Physics SSCP 2613. We will be analyzing the mechanical modeling and mathematical derivation of an automobile coil-over shock absorber systems. First, let's look at the problem statement for our assignment. We are tasked with evaluating a coil-over suspension device which is widely used in modern automobiles. The system relies on two main parts, a damper and a coil spring, where the damper sits right at the center. To focus strictly on the dynamic behavior, the question assumes the spring length match its unperturbed equilibrium length, meaning we can completely ignore the static downward weight of the vehicle for this scenario. Next, the core objectives of the prompt are divided into three parts. First, we must derive the analytical solutions to the governing second-order ordinary differential equations. Second, we need to select unit 3 decimal rational style constants to simulate displacements versus time graph across 4 distinct damping behaviors. And finally, we will discuss the practical engineering implication of those simulation results. Moving into our group solutions, we start with the fundamental physical derivations. By pairing Newton's second law, F equals to ma, and Hooke's law, F equals to negative ky, we can model an idealized frictionless systems. However, to account for real-world energy dissipation from the damper, we must introduce a retarding force that is directly proportional to the velocity. Combining these active forces and rearranging the terms give us our core second-order homogeneous linear differential equations, which is mass times acceleration plus our damping term and plus our stiffness term equals to 0. To solve this ODE, we divide through by mass and simplify the layout using standard abbreviations for natural frequency and our damping coefficients. Setting up auxiliary quadratic equations allow us to solve for characteristic roots which evaluate to negative p plus minus square root of b squared negative omega squared. The value of this discriminant mathematically determines our four physical damping regions. This step establishes our general algebraic equations for the overdamped, critically damped, underdamped, and entirely underdamped conditions. To make our solution entirely unique, we chose a mass of 1.080 times 10 power of 3 kilograms and a stiffness constant of 4040 times 10 power of 3 newtons per meter. Under critical damping conditions where L squared equals to 4 mk, our baseline damping constant M resolved to 43.598 times 10 power of 3. By doubling this value, halving it or dropping it to 0, we successfully generated our four concrete, distinct differential equations.
Hello, my name is Yao-Zhen, and I'll be going through the solutions for each of our systems. From an earlier slide, we've gotten the general equation, the general solution for the ODEs, and now that we have some values, let's plug them in and find the exact solution. So for an overdamped system, this will be its solution. The critically damped solution, this will be our system. For an underdamped system, this is our solution. And for an undamped system, this will be our solution. So here it is plotted in a graph using Desmos. This is the undamped solution, which will just keep oscillating forever. And here it is animated. As you can see, blue reaches equilibrium first, and then green reaches equilibrium next. And finally, after some time, even red will reach equilibrium. So the graphs of all four systems were plotted, and the critically damped system reaches the equilibrium state the fastest. The underdamped system will still oscillate between reaching equilibrium, and the overdamped system reaches equilibrium slower than the critically damped system, whereas the undamped system will continue oscillating forever. In terms of a car going over a bump with these systems, and the undamped and underdamped system will feel very bouncy and nauseating for passengers. The overdamped system will feel very stiff and sluggish, whereas the critically damped system provides the most ideal ride out of the four systems. Thank you very much.